Okay. So before going to today's class, let us just revise what we have studied in the last class. So in the last class, we have seen what is the principle of operation of a DC generator or a DC machine in general. So here, the DC generator or the DC machine will be the basic principle of operation is like dynamically induced EMF. Because of this dynamically induced EMF, the total operation of this machine is being done. And for when we come to the DC generator, the direction of the induced EMF, that is which is dynamically induced, is given by the Fleming's right hand rule. And so, in order to get all these things, what are the essential components? Means essential components are a magnetic field, a magnetic, the conductors or a group of conductors. In the motion of the conductor, the conductor should be rotating in a magnetic field. So, that is the basic requirement for this DC generator. So here we have seen what is the operation and everything. And again we have seen a simple loop generator, which is nothing but a single two conductors which are connected in a loop. And then what is the operation, how the EMF is being generated, that is how we saw. This is the different stages in which the conductor is being moved clockwise, such that how the voltage is being produced, that all we saw. And again we have seen that the EMF that is being produced is of alternating nature, but the name indicates it is a DC machine. So in order how to convert this produced alternating EMF to DC EMF, that is what we have seen. That is based upon the action of a component called as a commutator. This commutator will convert the produced AC to DC. That is what we have seen. What is a commutator and how the commutator is working principle and everything we have seen. Now, commutator is nothing but a mechanical rectifier. That is the main thing which we need to understand. Commutator is nothing but a mechanical rectifier. That is, it will rectify mechanically. It is rectifying through mechanical action. That's how this commutator works. Okay. So we just use this commutator for changing the alternating EMF which we got in the simple loop generator into direct voltage. That is the main purpose of using the commutator. Okay. So, and again we have some brushes. Brushes only connects the external load to the internal circuit. That's all. Brushes only connects the external load to the internal circuit. It will gather all the current that is being produced internally in the armature or internally in that single loop for this simple loop generator. In that loop, whatever the current that is being generated, that current will be taken out of the loop and then given to a stationary load which is outside the loop. Okay, that is the main use of the brushes. So this is what we have seen in the last class. And now we are going to see what is the construction of a DC generator. For today's topic, we are going to see what is the construction of a DC generator, how these are being constructed, what are the essential components which we need in order to construct a DC generator. This is the topic which we are going to see in today's class. Okay. So basically DC generators and DC motors have same general construction. So the general construction, whatever the components which we are assembling, will be common for both DC generators and DC motors. The only thing is, after only understanding which type of machine is required, only then we will be using the machine to work as a motor or a generator depending upon its application. Okay, so here he is saying, in fact, when the machine is being assembled, the workmen usually don't know whether it is a DC generator or a DC motor because the construction is similar. We just assemble all the parts together and make a machine. Okay, any DC generator can be run as a DC motor and vice versa. So we can run a DC generator as a DC motor or a DC motor as a DC generator by doing some adjustments. That's all. Okay. So all DC machines have five principal components. So any DC machine has five principal components. What are those principal components? Let us see. First one is the field system. That is, we know that there should be a field system. That is, there should be a magnetic field only in which we can convert mechanical energy into electrical energy, right? There should be a magnetic medium. In order to provide that magnetic medium, we have a field system. Again, we have armature core. Armature core is nothing but where these loops, where these conductors are being placed. A cylindrical construction will be there on which these conductors will be placed. That cylindrical construction is called as the armature core. And then those conductors which we are placing is nothing but the armature winding. Okay. Next is commutator. We have seen what is commutator. And next is brushes. So we have seen already commutator, brushes. All of this we have seen separately. Now we will be seeing them together. Okay. So this diagram for figure 1.7 will show you the basic construction of a DC machine. So here we'll be having different parts. Whatever the parts we have discussed, these are being put together like this. Now let us see each part separately. So the field system. So why do we need field system in this DC machine? Let us see. The function of the field system is to produce uniform magnetic field within which the armature rotates. So basically we need to have a relative motion between the field as well as the conductor. So that relative motion can be obtained by moving either the conductor or by moving the field. Right. So physically you can move the field around the conductor, like if you have a conductor and then if you have a magnet, then you can just move the magnet towards and away from the conductor. That way even the magnetic field of the conductor will be disrupted and then EMF will be produced. That is one way. The second way is you are putting the magnetic field constant and then we are moving the conductor. We are moving the conductor. So in this way also the magnetic field of the conductor will be disrupted and then the EMF will be produced. So depending upon the application, depending upon our convenience, we will be either moving the field or either moving the conductor. In this case, in this DC machine case, we are going to keep the field constant and then the conductors will be moving. We'll be keeping the field constant and then the conductors will be moving. So for this to happen, what we are going to do or how we are going to arrange this, we will see. Okay, so the main function of the field system is to produce a uniform magnetic field in which the armature rotates. So we need to make sure that we have a uniform magnetic field in which this conductors will be rotating and then EMF will be produced in that conductor. Okay, now it consists of a number of salient pole, of course even number, bolted to the inside of the circular frame, generally called yoke. So how the field system will be means, here you can see this is the pole. This is the pole. Okay. This is the pole. Okay. And again, these poles will be are connected inside the yoke. Yoke is nothing but the steel casing in which the whole machine is being arranged. Okay. This is the yoke is nothing but the steel surrounding in which the uh, machine is being what do you say, put together. This is the yoke. You can see this circular thing which you are seeing is nothing but the yoke. Okay. Okay. Next, here you are seeing the poles. Again, we have again we have here yours in the on these poles there will be a winding which is called as the field winding. There will be a winding which is called as the field winding. Let us see what this field winding is. Just a second. Okay, so that one is there. Next, the yoke is usually made of solid cast steel, whereas the pole pieces are composed of the stacked laminations. Okay, before understanding this, we need to understand a simple concept. Basically, we can use a permanent magnet. A permanent magnet is nothing but a magnet which is having a certain which is having permanent magnetism, like whatever the magnets which we have, like which we small magnets which we used to play with, all those magnets are called as the permanent magnets. That means they are already having magnetism in them. If if that we in order to create a magnetic field, we can use a permanent magnet or we can use an electromagnet. Electromagnet is a magnet where when you give the electricity to that magnet, only then it will work. If the electricity is not present, then the magnet will not be working. So we are going to use electromagnets in case of machines. Okay, why are we going to use electromagnets in case of machines? Means we can by controlling how much current is being given to that magnet, then we can also control how much field is being produced by that magnet. But when we come to the permanent magnets, these permanent magnets have a constant field. That means whatever the magnetic power that is there for that magnet, only that will be present for the whole system, for the whole time. If you want to change or if you want to increase or decrease the amount of magnetism produced by the magnet, then we need to go for the electromagnets. Electromagnets are nothing but the ferromagnetic materials which are wound by a wire. Okay, so that wire, when electricity is passed through that wire, because of that electricity, the magnetic power of that magnet will be controlled. So if you want less magnetism, we are going to give less current to the electromagnet. If we want more magnetism, we are going to give more current to the electromagnet. So just by understanding this, so by taking this, we can just create whatever the field we want, whether we want large field or the small field, we can create based upon how much of current we are giving to the electromagnet. So here whatever you are seeing, these poles are nothing but electromagnets. These electromagnets will be given some current through an external source, and then we are going to get the magnetic field which is required for us to operate in. So the here he is saying that the yoke is usually made of solid cast steel. So this circular thing which you are seeing, this yoke outside thing which is there, this casing will be a solid thing. Whereas these poles which are there, those will be of stacked laminations. Laminations means small layers, small thin layers will be there. The material will be cut into small thin layers and then they will be put together. Similar to a wafer, we usually eat wafers, right? In that wafers, we'll be having thin layers which are being put together with a cream or something, right? Similar to that, these laminations are present. Here we are going to take a material and then cut it into very thin layers, and those thin layers will be stuck together, will be put together to form a uniform material. Okay, so that is how the poles are made. This yoke is the solid steel material, that is it will be normal whatever thick material which we have, but the poles will be stacked laminations. Those will be stacking. We are going to divide it into small thin layers, and then those layers are put together. That is what is called as the stacked laminations. Field coils are mounted on the poles and carry the DC exciting current. As I said earlier, these poles will be having field coils. That is, there will be a electrical winding around the pole. These windings will carry DC current. Okay, these windings will carry DC current, and then whatever the amount of field which we need, that can be controlled. Okay. Next is the field coils are connected in such a way that the adjacent poles have opposite polarity. So basically by changing the direction of winding of the field coil, we can change the pole that is being formed on that pole. We can change the whether it is a north pole or south pole. This you people might have already studied, right? In your magnetic circuits, you might have known that by just changing the way which we wind will tell you what pole is being generated in that material. Okay, in that material, what pole can be generated will be depending upon the way you wind it. So we need to make sure that alternate poles are being produced in the adjacent. Alternate poles are formed between the adjacent poles. Like if you have here you have north pole, so we need to make sure that the winding is such a way that this is a south pole. Okay. Okay, so here if you are getting a north pole, it should, the adjacent pole should be always opposite to whatever is there in this one. So if you are having north here, it should be south here. If you are having south here, it should be north here. Okay, so we need to make sure that the winding of the field winding is such that there will be opposite poles produced in the adjacent poles. Okay, the MMF developed by the field coils produces a magnetic flux that passes through the pole pieces, the air gap, the armature and the frame. So basically what will happen here means, because of this electromagnet, will be having different, we have seen, right, will be having a north pole, a south pole, depending upon what type of winding we have. This flux will be present, right, this magnetic flux will be produced. How we have electromotive force, right? Electromotive force, EMF, is nothing but the force which will generate the electricity, right, generate the current. That is, it will push the electrons to move from one point to another point, right, because of the change in EMF. That is, if the concentration of electrons is more at one point and the concentration of electrons is lesser on that point, there will be a potential difference between those 2 points, and then the current will be flowing from higher potential to lower potential. This we know, right? In the same manner, in order to make sure that the magnetic lines of force, that is magnetic flux, is moving from one point to another point, there should be some external force, not external, some change by which this force is, by which this magnetic lines of force are being driven, right? That change, that difference is nothing but the magnetomotive force. How we are saying electromotive force for EMF, for the, in case of electricity, we will be having magnetomotive force in case of the magnetic circuits. So this magnetomotive force will force the magnetic lines of flux to pass through, to go to one place from another place, to go, it will force the the magnetic flux to move from one point to another point. So that EMF will be developed in the field coils, which will, this sorry, that EMF will be developed by the field coils, which produces a magnetic flux. That is, magnetic flux in magnetic circuits is analogous to current in electrical circuits. Okay, when we see the analogies between magnetic circuits and electrical circuits, for the electrical circuits, EMF is present, right? That EMF is analogous to MMF in magnetic circuits. That will drive the magnetic lines of force to move from one point to another point. Okay, in EMF will be driving the current to from one point to another point in case of EMF. Here magnetic flux will be driven by MMF. Okay, in case of magnetic circuits. Similarly, current which is there in electrical circuits is analogous to magnetic lines of force, that is magnetic flux in magnetic circuits. So those are the analogies. Okay, so in order to make sure this magnetic flux is moving from one point to another point, there should be an MMF that will be developed. That MMF will make sure that this magnetic flux will pass through pole pieces, air gap, the armature and the frame. So sorry, here you can see pole pieces. In these pole pieces also we'll be having the MMF, and again pole pieces, air gap. Air gap is nothing but the gap between the rotor and this pole. This gap which is there, this gap which is present, the small gap, this green color gap, that is called as the air gap. So the MMF will make sure that the magnetic lines of force, magnetic flux, passes through poles, air gap, armature. Armature is nothing but this one. This one. This is the armature. This is the armature, and again this is the yoke. So the magnetic lines of force, that is the magnetic flux, will be passing from pole, air gap, armature as well as yoke. Okay, so that forms a complete circuit for the magnetic lines of force, that is the magnetic flux. Okay, here in this diagram he is showing us how the flux will be moving. So here you can see this is the poles, these are the poles, this is the poles, and again we have this is the armature, this gap, air gap is there, sorry, here the air gap is there, and again we have this core or the yoke. Okay, so we have poles, air gap, armature, as well as the yoke. So we have all the circuit will be closed here. Okay, so this is yoke, we have poles, armature, air gap. So we have all 4 points which were discussed, which were said where the magnetic lines of force are moving. Okay, so that is what we have seen. Next is practical DC machines have air gaps ranging from 0.5 mm to 1.5 mm. So he's saying that the mmf the air gap is having 0.5 mm to the air gap which we have will be 0.5 mm to 1.5 mm. Since the armature and the field systems are composed of materials that have high permeability, most of the mmf of the field coils is required to set up the flux in the air gap. So basically what happens here is we are going to make sure that the permeability is nothing but the nature of the element by virtue of which it allows the magnetic flux to go through it. Okay, how we are going, we have already seen what do you say, resistance and all those things, right? Resistance is the virtue of by which the material opposes the flow of current. Like that, this permeability is a what do you say, property by which the what do you say, magnetic lines of force will be flowing through the material. Okay, if you have high permeability, number of magnetic lines of force it can allow through the material will be high. So we are going to make sure that the armature field systems will be making sure that the armature and the field systems will be having high permeability, that is it will allow many what do you say, magnetic lines of force through them. Okay, most of the mmf of the field coils is required to set up the, basically because of this high permeability nature, the mmf, that is the driving force which is required to drive the magnetic lines of force in this, in these, that is armature and field systems, will be less because it is already having the high permeability, that is it is allowing the magnetic lines of flow force to go through it easily, right? So here, because of that nature, we need not to put lot of mmf into that, like that is we need not to make sure that more mmf is present in case of armature and then field. So the maximum amount of mmf where we require the maximum amount of mmf means we require the maximum amount of mmf in the air gap to set up the flux in the air gap, that is we need here in the small air gap which we have, there is no permeability. Okay, there will be no permeability. So in order to make sure that the flux is present there, we need to give in more more mmf. Okay, so in order to set up in the air gap, so for the air, for the what do you say, flux to be present in the air gap, we need more mmf. So most of the mmf that is being produced by the field will be used to set up the magnetic flux in the air gap. By reducing the length of the air gap, we can reduce the size of the field coils. So if you are reducing the length of the air gap, that is he has given us the air gap as 0.5 mm to 1.5 mm, right? So if we can further reduce the air gap, that is 0.5, if we can make the air gap as 0.5 mm, then the size of the field coils will also be reduced, because we don't need much mmf to, if we don't have much air gap, we don't need much mmf, simple. So the field coils which we are using might be reduced. The field coils might be reduced. Reducing the size of the field coils means the number of turns on the field coil can be reduced. The number of turns on the field coil can be reduced. That is, based upon the number of turns, how many turns are there in the field coil, the strength of that magnet will be present. Okay, so we know that if there are more number of turns, then more amount of mmf can be produced. So if you don't need that much of mmf, what we are going to do is we are going to reduce the number of turns which we are putting on the pole. So that is the field system. Now we are going to see the next topic, which is the armature core. We have 5 essential topics in that. The first one is completed, that is the field system is completed. The second one is the armature core. So armature core is keyed to the machine shaft and then rotates between the field poles. So here you can see the armature core. So this will be the armature core. So this is the armature core. This is the shaft. I'll show you. Wait. This is the shaft. This is the armature core. Okay. So the armature core will be given to the armature core will be put on to the shaft. So this is the armature. Sorry. So this is the armature and this is the shaft. Okay. It consists of a slotted soft iron laminations of about 0.4 to 0.6 mm thick that are stacked to form a cylindrical core as shown in the figure. So what we are going to do is, in the similar manner how the pole is being stacked, here also we'll be having laminations which are of 0.4 to 0.6 mm thick, and then those laminations are put together to form a cylindrical core. Okay, that is what he's saying. So soft iron laminations, what is the material that is being used means soft iron is the material that is being used. Those soft iron laminations are put together in or stacked to form a cylindrical core. Okay, here in this cylindrical core also there will be slots. It will be like this, the slots will be there. In these slots we will be placing the armature windings. In these slots we will be placing the armature windings. Here the armature windings will be placed. Okay, so here whatever you are seeing, the laminations will be of this sort. These are nothing but the laminations. Okay, these are how the laminations will be. These type of laminations are put together to form a cylindrical core. Okay, the laminations are individually coated with thin insulating film so that they do not come in electrical contact with each other. So in order to make sure that these are not having electrical contact, that is, they, in order to make sure that they are not forming a circuit by themselves, we are going to put an insulating film, an insulation between each of the laminations, an insulation between each of the laminations. The purpose of laminating the core is to reduce the eddy current losses. Okay, so basically what happens if you don't laminate the core means, if you do not make a thin slice of the core and then put together, the total core, if the total solid material is used, then there is a formation of a complete circuit, complete electrical circuit in that core itself, where because of which there will be currents flowing in the in that material itself, and then because of those currents cannot be tapped back, those currents cannot be tapped outside. So because of that, what happens is there will be a loss in the electrical energy that is being produced. That type of loss is called as the eddy current losses. Okay, so in order to make sure that there are no eddy current losses, we are going to laminate the core. We are going to make thin layers of the material and then put together such that, and even while putting together, there is a thin insulating film between each of the laminations. From one lamination to another lamination, we have a thin insulating film, so that there will be no electrical contact between the two layers of the laminated core. Okay, the laminations are slotted to accommodate and provide mechanical security to the armature winding, and to give shorter air gap for the flux to cross between the pole face and the armature teeth. So in order to make sure the air gap which we are having between the rotor and rotor, here whatever the air gap is there, this air gap, in order to reduce this air gap, as well as in order to make sure that these windings which we are going to place are having mechanical constant or mechanical security, these laminations are slotted. So what we are going to do here is, here we are going to place a winding like this. Here we are going to place a winding, here also we are going to place a winding. Like that we are going to place windings in these slots. Okay. So now what happens is, now the pole will be something like this, right? The pole will be of something like this. Now what happens? So we have a pole, so we can reduce this air gap. We can reduce this air gap, as well as we can make sure, these these windings which we are placing do not get out of the material, so do not get out of the slot, right? So in order to make sure all of these things, we are going to have slots in the laminations. Okay, so this is the armature core, because this is the nature of the armature core. Now next thing is armature winding. So the slots of the armature core hold insulated conductors that are connected in a suitable manner. So what we are going to do is, as I've explained earlier, we'll be having a slot in which the armature winding is going to be placed. So these armature winding will also, each armature winding will also be again insulated from another winding. That is, in that slot we can put one winding or two windings depending upon the nature of the windings. Okay, so if we are having one winding, even then that will be insulated, because the current which will be produced should flow only through the winding, not the other parts. So in order to make sure that the current is flowing only through the winding, we are going to insulate the winding and place it in the slot. Okay, this is known as the armature winding. That is what is saying. Okay, this is the winding in which working EMF is induced. That is what we are saying. In this windings only the EMF will be induced. The armature conductors are connected in series parallel. The conductors being connected in series so as to increase the voltage, and in parallel path so as to increase the current. This we know, right? If they are connected in series, the amount of voltage that is being produced will be increased. If they are connected in parallel, the amount of current that is being flowing through these conductors will increase. We know this, right? So these armature conductors, that is the armature conductors which we are placing in each of the slots, will be connected in series as well as parallel, series parallel. Why we are connecting them in series means, in order to make sure that uh, the EMF is greater, we are going to connect them in series. If we are going to connect these series connected things in parallel, so that there will be higher amount of current that can be extracted from the circuit. The armature winding of a DC machine is a closed circuit winding. So the conductors are being connected in a symmetrical manner, forming a closed loop or a series of closed loops. So here what will happen is, these loops, there will be loops forming. There will be, these armature windings will be in a loop form. That is, a closed circuit will be, a closed network will be formed when these loops are being connected together. So that, how are we going to do it? We will see in the later class. Okay. So that is the armature winding. The next topic is the commutator. Already we have seen what is the commutator action and everything. So a commutator is a mechanical rectifier which converts the alternating voltage generated in the armature winding into direct voltage across the brushes. Right? We know this. The commutator is made of copper segments insulated from each other by mica sheets and mounted on the shaft of the machine. So let us see how they are mounted. Like this. He's showing us the commutator. This is the figure 1.11. Here you can see it. This is the mica sheets, and then these are the commutator segments. These are the commutator segments. In this black line which we are seeing is nothing but the mica insulation, and this are slots which you are seeing are the commutator slots. Okay, the armature conductors are soldered to the commutator segments in a suitable manner to give rise to the armature winding. Actually, when we have seen a commutator, we have seen only two parts, right? C1 and C2 sections will be there, and then one conductor will be connected to C1 section, and the another conductor will be connected to the C2 section of the commutator. This we have seen in the last class. Similarly, just imagine if there are n number of conductors. If there are n number of conductors, then the commutator will be divided into n by 2, that is half, right? So such that each conductor will have a separate piece of commutator. That's why in this diagram, if you see, there are number of segments of the commutator. Each segment will be connected to one of the conductors. Okay. That's what he's saying here. Are soldered to segments in suitable manner to give rise to the armature winding. That is what he's saying. Okay. Depending upon the manner in which the armature conductors are connected to the commutator segments, there are two types of armature winding in the DC machine. So basically, depending upon how these armature conductors are connected to the commutator segments, how they are being connected to the commutator segments, there are two types of armature windings. The first one is called as the lap winding. The second one is called as the wave winding. First one is called as the lap winding. The second one is called as the wave winding. We'll see what is lap winding, what is wave winding, how they are differing from each other. What happens if one is when one is connected? That if we have a lap winding, what will happen? If we have a wave winding, what will happen? We'll see in the consecutive classes. Okay. Next, great care is taken to build the commutator because any eccentricity will cause the brushes to bounce, producing unacceptable sparking. So we need to make sure that the commutator is being built very securely, because if that doesn't happen, it will lead to sparking and maybe eventually the machine will blow up. So we need to make sure. The sparks may burn the machine and overheat and carbonize the commutator. That's all. It may damage the total commutator if it is not taken care of. Okay, that is the commutator. The last part is the brushes. The purpose of the brushes is to ensure that the electrical connections between the rotating commutator and the stationary external load circuit. So basically, it will make sure that there is an electrical connection between the rotating commutator and the external load circuit. The brushes are made of carbon and rest on the commutator. So they'll be resting on the commutator, and these are made of carbon. The brushes pressures is adjusted by means of adjustable springs. Here you can see a spring, right? 1.12, the figure 1.12. Here you can see the springs, right? This is also a spring and this is also a spring. So based upon how you want to connect the brushes, how much you want to push the brushes to the commutator, that can be um, sorry, that can be adjusted by these springs. Okay, if the brush pressure is very large, the friction produces heating of the commutator and the brushes. That's what we are saying. Okay, in on other hand, if it is too weak, the imperfect contact with the commutator may produce sparking. So it should not be too harsh on the commutator and again too loose on the commutator. If it is harsh, then it will produce heat that will lead to sparking. If it is too weak, that may produce sparking. Okay, multiple machines have many number of brushes as they have many number of poles. So based upon how many poles are present in the machine, that many brushes will be present in the machine. For example, a 4-pole machine has 4 brushes. We'll see how these are being done and everything. Okay, as we go around the commutator, the successive brushes have positive and negative polarities. This we know, right? There will be one positive brush, there will be one negative brush. Brushes have the same polarity of brushes having the same polarity are connected together so that we have two terminals, that is the positive terminal and then the negative terminal. So if we have 4 brushes, 2 brushes will be positive, 2 brushes will be negative, right? So those two positive brushes will be again connected to a terminal, as well as the negative brushes will be connected to another terminal, such that at the end we have only two terminals, that is one positive terminal and one negative terminal. So this is the general construction of which we have already seen. Again, we are seeing the total construction of the DC machine. So